Okay, we'll get started. So we stopped last time at on this slide. We were talking about equivalent circuits and why we would use equivalent circuits. And we started and we tried to do an example. We talked about one of the two types of equivalent circuits that we would discuss. So we talked about what is called the Thevenin equivalent circuit last time. And with the Thevenin equivalent circuit, we said that the result that we want to achieve is put this big circuit in a box and then bring two terminals out. And from these two terminals, I would like to build a representation for what's inside this box. Why do you want to build a representation for what's inside this box? Because if you want to connect a specific device to your big circuit, you want to look at the effect of that big circuit on that specific device. You don't care what's happening inside that big circuit. So you come up with what is called a Thevenin equivalent circuit for that system. Yeah. And the Thevenin equivalent circuit for any electrical circuit basically is composed of a voltage source, which we call V Thevenin, and a resistor in series with that voltage source. And these would be the two terminals that we are looking into or at connecting our new device to. Okay, so and last time we said, okay, how do we find this value R Thevenin and this value V Thevenin? We said that the value V Thevenin is basically, if this is our original circuit, we would have to solve the original circuit and figure out what the voltage is between these two terminals, or the open circuit voltage between these two. So these are two terminals. The open circuit voltage between these two terminals is what is called the Thevenin equivalent voltage. And to find the value for R Thevenin, or this equivalent resistance to this big network that we have inside our box, what we would do is place a short circuit across the terminals. You place a short circuit across the terminals, find the short circuit current, and then from knowledge of the short circuit current and the open circuit voltage, you have a relationship between the open circuit voltage and short circuit current and this value of resistance, which is R Thevenin. Okay, so it's Ohm's law. The relationship is Ohm's law. So we went through this example last time, and let's look at another example. That's where we left off, I believe. Or before we look at the example, okay, so the way we found R Thevenin, was through this short circuit, so through placing the short circuit and finding the short circuit current. Okay? And then from the open circuit voltage and short circuit current, we found R Thevenin. There's another way to find R Thevenin for circuits without dependent sources, right? Dependent sources are sources that have, like if this is a source that depends on 15 times V of R1. It's called a dependent source, right? In this case, it's the value for this voltage is 15 volts. So it's an independent source. It does not depend on any other parameter in the circuit, right? So we looked at some dependent sources and independent. So if the circuit has independent sources, there's a quicker way to come up with R Thevenin. Instead of finding the short circuit current, open circuit voltage, short circuit current, dividing them by each other and finding R Thevenin, the way that you can do it if the circuit only has independent sources, is you basically turn off the sources. So turning off the sources meaning if you have a voltage source, it will produce no voltage. If you have a current source, it will produce no current. The current will be an open circuit, the current sources will be open circuits, the voltage sources will be short circuits. Let's apply that here. Okay? If we apply that trick here, so I said that as if you don't have a source. So as if this voltage source is providing a voltage of 0. Voltage of 0 means it's a short circuit, right? So I will place a short circuit instead of this source, and then I end up with what? These two resistors are what? Series or parallel? What? Parallel. Remember, my two terminals are here. This is one terminal. This is my other terminal. I want to find the equivalent Thevenin resistance between these two terminals. So one way is what we discussed last time. Find the open circuit voltage, find short circuit current, divide open circuit voltage by short circuit current, and you will find R Thevenin. You take that R7 and you plug it in your equivalent circuit. That's one way. The other way is if your circuit contains only independent sources, like a voltage of 15 volts, a current of 1 amp, specific independent values that don't depend on other parameters in the circuit, what you can do is turn off the source. So if it's a voltage source, make it produce 0 volts, meaning it's a short circuit. If it's a short circuit, then it's like these two resistors are in parallel. So the equivalent resistance is 50 ohms times 100 ohms divided by 150. Right? So what's 50 times 100 divided by 150? Calculator or brilliant mathematician? Huh? It's 33.333. I know the answer because but it's a third, right? It's a third of it. So it's so we get the R Thevenin without having to find the short circuit current, right? So that's the other way of doing this. Only if the circuit has independent sources. If it has dependent sources, you cannot. You have to go through the procedure. Right? Find the open circuit voltage, find short circuit current, and then the R Thevenin will be the ratio between them, using basically Ohm's law applied to the equation. Okay, so that's what this slide says here. That when the original circuit has no dependent sources, you can apply this trick. Yes, sir. No, the objective is to find the equivalent Thevenin equivalent circuit. I don't care about the short circuit current. You can find it now since you have the open circuit voltage. So since you have Thevenin equivalent voltage and Thevenin equivalent resistance, just divide the voltage, the Thevenin equivalent voltage, by the Thevenin equivalent resistance, right? So here. If you have V Thevenin and R Thevenin, and you want to find the short circuit current, it's basically this. It's the current flowing in this circuit, which is this voltage, V Thevenin, divided by R Thevenin. Now, to find the Thevenin equivalent voltage source, you still have to solve your circuit. Like we had the circuit. Let's look at our circuit. Go back here. I go back here, right? To go back here, remember the objective is to find the Thevenin equivalent circuit for this system here, looking from these two terminals. Everything inside here, I want to find an equivalent Thevenin equivalent circuit for. The Thevenin equivalent circuit, I know how it looks like. It looks like a voltage source with a resistor in series. I know that for a fact. But I don't know R Thevenin yet, and I don't know V Thevenin. The only way to find V Thevenin is to look at the open circuit voltage here. No, there's no trick. There's no similar trick to find V Thevenin like R Thevenin. No, there isn't. Good question. R Thevenin, there's a trick to find it quicker. V Thevenin, no, you have to solve the circuit. You have to find the voltage, open circuit voltage between the two terminals you are looking into. Okay. I think the next one will be an example. They just go through the procedure, so we will not read the procedure. We will just go through an example. Okay, find the equivalent, find the Thevenin resistance directly, then find the short circuit current, and then the Thevenin equivalent circuit, right? So I went through a bunch of hoops here. So okay, so this is my original circuit. I'm looking through these two terminals, right? These are my two terminals. So I need to go to this Thevenin equivalent circuit here. right? The only way to do this is to find the open circuit voltage between these two terminals, and then to find the resistance. Do I have any dependent sources here? This is 20 volts, and this is 2 amps. They're all independent. They are both independent sources. So since they are independent sources, I can apply that trick. That trick will help me find R7. So this is a short circuit. How about the current source? Open circuit. It cannot provide current. If it's a short circuit, it will provide a path for current to flow, right? So it cannot provide any current. I cannot erase. Oh, I cannot erase the point. Then I can make it current. I like to play with it. Yeah. Okay, so current sources are open circuit. So current source, open circuit. Voltage source, short circuit. Right, so I do that, and then I can find the equivalent resistance between the terminals of my circuit now. So what do I have? I have simply 5 ohms in parallel with 20 ohms. Right? So the equivalent resistance would be 5 times 20 divided by 25. 5 plus 20. Right? So this is my circuit now after removing the sources, and then equivalent resistance is the parallel combination between 5 and 20, right? And the result is 4. We know it's right because it's less than both resistors connected to the individually. So 4 is what I have, and I will plug right now into my Thevenin equivalent circuit. Because I know what the Thevenin equivalent circuit is, voltage source and resistance. Now I know the value of the resistance. For me to know the voltage source, I have to solve the circuit. I don't have a choice, right? So for me to solve the circuit, what do I need to do? This is a little bit tricky, right? So I have a current source. Forget about this short circuit for now, right? I have a current source across here. I don't know what the voltage is across the current source. Right? I have no clue. There's no impedance. So the current source, there's no voltage drop across a current source as such, right? So this circuit's a bit tricky. So we will learn something else that will help us transform any current source with a resistor in series. But short of that, what else can we do to find the open circuit voltage? I know that there's a relationship between the open circuit voltage and R Thevenin and the short circuit current. This will always be there. Remember, because again, if I put a short circuit here, then this is my short circuit current. So, excuse me. Yeah, so I will use this trick to do what? To define, to put and place a short circuit across my circuit here. If I place a short circuit across here, and I find this value of short circuit current, then I know my R Thevenin, I will know my short circuit current, and hence I will be able to calculate V Thevenin, which is the open circuit voltage. Right? So I did not. This circuit's a bit different than the one before. Before we were able to easily solve for the voltage across the our two nodes at the input, right? Because I didn't have a current source across it. But because you have a current source across the two inputs now, there's no voltage drop as such across a current source, right? So since there's no voltage drop across a current source, then we have to find another way to solve and figure out how to calculate V7. Right? There will be this method, and then there will be another interesting method we'll talk about. We'll be able to convert this current source with a resistor in parallel to a voltage source with a resistor in series. And that's what's called the Norton equivalent circuit, right? We have a Thevenin equivalent circuit, and we will have a Norton equivalent circuit. The Thevenin equivalent circuit it looks like this resistance and voltage source in series. We will see what the Norton equivalent circuit looks like. But here I'm trying to find the Thevenin equivalent circuit, so I cannot find a way to solve it easily, right? I don't know what the voltage across these two nodes are because I have a current source here. So what we do is we know the relationship between V Thevenin is equal to R Thevenin times I short circuit. So this is my I short circuit. I know R Thevenin. I want to find V Thevenin. So this I short circuit is the same as this I short circuit. It's the same. Right? Since I'm trying to find an equivalent to whatever's inside this box, then if I put a short circuit around the box, it's the same as putting a short circuit around the equivalent. Right? So these two are the same. So if I find this, I should be able to go and substitute in this relationship. Right? So to find this, what is the current flowing in this branch? So there's current flowing from this current source here, coming this man. It's like a current, it's a constant flow pump, constant flow rate pump, right? A constant flow rate pump will regulate its pressure and keep a certain flow rate. It's exactly the same. It will push current, and it will have, internally it's a voltage source, of course. Internally it has to have a voltage source, right? It's a voltage source, but it's a controlled voltage source to maintain certain flow rate, to maintain certain current. If I look at the fluid analogy is the same. There you have constant pressure pumps, and you have constant flow rate pumps. It's the same. A constant flow rate pump requires pressure. I mean, if you have no impedances to the flow, the pressure internally in the pump will be low. But if you have impedance to the flow, to maintain the same flow rate, the pump will have to raise its pressure. When we do nodal analysis, the voltage at the two terminals of the current source, it's like the voltage at the two terminals of the voltage source. There we cannot define the current inside, right? Good question. Okay, so now we have to do Kirchhoff current law to be able to solve this circuit, for example. So let's apply Kirchhoff current law. Current is coming into this node from here. Current is coming into this node from. So this is all one big node, right? This is all one single node that we have here. We have current coming in from here, coming out from here, current in coming here, and then current coming out of the nodes here as well. Okay, so let's on the next page. So basically, I'm gonna take I1, add it to 2 amps. These are the currents coming in. So I1 plus 2 amps is going to equal I2 plus I short circuit. Correct? This is my Kirchhoff current law at this node. What else do I know? This short circuit is placed across the parallel, anything in parallel with it, right? So it's placed across this current source, and it's placed across this resistance. Is it going to affect the current in the current source? No, the current source will always produce this same current, right? But if I place this short circuit across the resistance, is there any current? Will any current flow in the resistance? You have this short circuit here, right? Current coming in here, we'll see what? Remember, current coming in into a node will be divided up, right, depending on current divider rule. Current divider rule says that the amount of current flowing in one branch will depend on the impedance of the other branch to current flow. This short circuit has no impedance to current flow. It will allow all the current to flow through, right? So all the current coming in here will actually flow through the current source, and the current coming from this current source as well will be added to it, right? Because here I have no control. This is a constant flow rate pump. It will always push water through. It will always be pushing. It will never take in any of the current. The current will not flip the polarity in this branch. The polarity of current in this branch is 2 amps. It is dictated by this constant flow rate pump, right? So that means that I2 is what? I2 is the current here. What is I2? It's 0. So I2 will be 0. So basically I have I1 plus 2 is equal to I short circuit, So now I need to find, I1 and I short circuit. So if this is 0, then this doesn't exist, right? So current is coming in from this branch, in from this source, and then through this resistor, and I have one loop here, right? So current is coming in here, I1, and I have 2 amps coming in from the current source, and that is equal to I short circuit. Let's see. This is what we were referring to, the fact that to find I short circuit, we know that VR2 is 0, R2 is this resistor here, right? There's no current flowing through it, so the voltage across it is 0, right? So this, the VR2 is 0, and we're still finding the Thevenin equivalent voltage. I don't know what this was. Anyway, we were applying Kirchhoff current law, right? So we were applying Kirchhoff circuit. I short circuit plus I2 equals 2 amps plus I1. I1 is equal to what? I1 is the current flowing in here, right? I have a short circuit here. Right? This short circuit, I mean, whether I put it here or here does not really matter. So what current is flowing in this loop? This is short circuit current. Short circuit current now, I short circuit, is equal to what? 2 amps plus I1. I need to find I1. So how do I find I1? I have a loop here that basically this resistance does not really exist anymore. It does not exist for me. So, and I have a closed loop here. Right? I have a closed loop here. I can basically, this voltage source divided by this resistance will tell me what the current is in this branch. Right? So it's 20 volts divided by 5 ohms. It will tell me this I1, value for I1. This I1 is added to the 2 amps current source, and they are both pumping current into this short circuit that we have. Okay? So what did I find? I found now my short circuit current equal to 6 amps. If you have the short circuit current, and remember this was a circuit with independent sources, so I can find my R Thevenin by doing what? By short circuiting here and open circuiting the current source. That's what I did here. Short circuit the voltage source, open circuit the current source. So the equivalent Thevenin resistance is the parallel combination of these two. So I have R Thevenin and I have I short circuit. And the relationship between the quantities in Thevenin equivalent circuit is that V Thevenin is equal to R Thevenin times I short circuit. So now I have R Thevenin, now I have I short circuit, so I can calculate V Thevenin. Okay? Yes? Yes? We saw that we didn't like dealing with the current source, right? This current source is a bit of a nuisance, right? The idea of having a current source at the output is not very pleasant, and we didn't like combining it with a voltage source. So sometimes it's easier. I mean, sometimes it's just easier to find a different way to represent a certain portion of the circuit. So, for example, we represented a certain portion of the circuit using a Thevenin equivalent circuit, right? And it was basically a voltage source with an impedance or resistance in series. Now we will talk about a different representation. This is still Thevenin, sorry. I thought we were talking still in representation. Still another example of Thevenin equivalent circuit. Sorry. Norton will come. So let's go through this example as well quickly. So, but what's the difference between this example and the last one? Yeah, the current source here is dependent, right? So I cannot open circuit the current sources, short circuit the voltage sources to find R7. How do I find R7? I have to find the open circuit voltage and the short circuit current, and then divide them by each other to find the R7. Right? That's the difference between this example and the previous example. Right? So let's go about that. So let's see what we're doing. So first we try to find Thevenin, which is the open circuit voltage. We use nodal analysis. So this is our ground or reference. Typically we do that we use our negative supply terminal for the battery as our reference, since we want to measure things voltages with respect to it. So it's not really matter. And then we want to find the open circuit voltage. So how do we do that here? We want to basically find the node voltage here. So you can apply Kirchhoff current law, right? So the voltage here is V open circuit, right? That's the voltage that we want to find here, right? This is V open circuit voltage with respect to my reference. So this node here carries V open circuit voltage. So V open circuit divided by 10 ohms, that's current flowing out of this node, right? This current source is dependent current source is pushing current this way, and they have defined Ix this way, right? So whatever is coming into the node is whatever is coming out of the node, right? So 2Ix plus Ix, which is this current here, is equal to V open circuit divided by 10 ohms. Right? So that's Kirchhoff current law applied at this node up here. Right? So V open circuit over 10 is equal to 3Ix. So they solve for Ix, so Ix is 10 minus V open circuit divided by 5. Where Ix is 10 minus V open circuit divided by 5. No, I think Ix is given. 10. Excuse me? Exactly. Good point. So where did they get this from? Good. Where did they get Ix from? What he said was right, but I want to see who paid attention. So what is Ix? How did they get this? We defined Ix in this direction. Right? So it's positive is here. This is a resistor. Right? So positive is here, negative is here, and this is all one node. Right? So Ix is equal to 10 volts, which is what we have at this node here, minus what we have on the other side of the resistor, which is open circuit voltage, divided by the value of the resistance. Very good. Right? So I have Ix, and given Ix in terms of the open circuit, I can substitute in the equation that I just calculated here from Kirchhoff current law at the node, and solve for the open circuit voltage. Very good. Yes, ma'am. The voltage divided by, 1 second, let's go to the big. No, because here I had a short circuit here. Remember, this is there was a short circuit here. Now I still don't have that short circuit. I'm solving this. We were solving for the short circuit current. That's why this resistor was short circuited, and we were able to find the current I1 as 20 divided by 5, right? Because we had the short circuit. We placed the short circuit here, but now we were still finding the open circuit voltage. We were still trying to find the open circuit voltage here. In this example, we were calculating the open circuit voltage, and the open circuit voltage was calculated in terms of Ix, right? My circuit is still open, right? So this Ix, when these two nodes are open, is equal to the voltage on one side of the resistor minus the voltage on the other side of the resistor. Okay, that's 10 here, and then open circuit voltage on the other side. Good point. So now I have my open circuit voltage, and I still have dependent sources, so I cannot do simplifications. What I need to do is place a short circuit now. Now is going to be very similar to the previous example. Okay, this part will be similar, right? I put a short circuit here, and then figure out what current is flowing in this short circuit. So, is any current going to flow in this resistor? No, there's a short circuit across this resistor. So this resistor is not there, right? So current will flow from Ix and 2Ix into the short circuit, right? So what is Ix equal to? We calculated it here. 10 minus V open circuit divided by 5. Open circuit voltage is 8.57, so I know Ix. So I know Ix, I add it to 2Ix, and that's what's flowing in my short circuit. Given short circuit current and open circuit voltage, you divide V by I, and you will get R7. And that's what you will plug here. Okay? Another example. Same as no, this is the solution to the previous example. The other equivalent circuit that we said we will introduce is it's called Norton equivalent circuit. So this box that we have with two terminals outside, we were able to represent it with a voltage source and a resistor in series. Okay. The other way we can represent it is a current source with a resistor in parallel. That's the other representation of that box. Because that box at the end of the day will have some voltage, potential difference or voltage across the terminals, and if you put a short circuit, current will flow. So same thing here. I have current flowing here. If I put a short circuit here, if I put a short circuit around this box, what's going to flow? This Norton equivalent current will flow, right? And if I have an open circuit here and I connect something here, this other circuit that I have will affect the current flowing here in this resistor, and hence I will have a voltage across, right? So I can either represent my block or box, a black box, as a Norton or a Thevenin equivalent circuit. Sometimes you would want to do this, sometimes you would want to do that. In the example that we had where we had a current source at the output, we didn't want to deal with that, right? So in that case, we will find a way to convert between the Thevenin equivalent circuit and the Norton equivalent circuit. So let's first see what the Norton equivalent circuit looks like. Looks like current source with this resistor in parallel. The resistor R Thevenin is the same R Thevenin that we had before. So given a circuit, this RT here in the Norton equivalent circuit is the same. Same value, same process to find R Thevenin. And the Norton equivalent current, or the Norton current, is nothing but the short circuit current that we were calculating before. Right? So hence the relationships between these circuits is also governed by V equals I times R. So the open circuit voltage of the circuit will equal the Norton current multiplied by the Thevenin equivalent resistance. Right? So if you want to convert the Norton equivalent circuit to a Thevenin equivalent circuit, how would you do that? It's the same R Thevenin, right? And I would take my I Norton multiplied by R Thevenin, and this will by R Thevenin, this will be my Thevenin equivalent circuit, Thevenin equivalent voltage. And if you want to find the Norton equivalent circuit from a Thevenin equivalent circuit, you take your Thevenin voltage divided by R Thevenin. You will find your short circuit current, which is exactly the Norton current, right? So if you have, anytime you see a resistor in parallel with a current source, you can convert it to a voltage source series with a resistor. Sometimes it will help you simplify circuits. We will do an example. We'll do examples like that. So as we were saying, the Norton current that we have in the current source here is nothing but the short circuit current that our circuit in the black box is producing. And RT can be found the same way as the Thevenin equivalent circuit. we describe the process, and we will just go straight to an example. The example says, find the Norton equivalent circuit for this big box here. I have a big box inside, inside which I have a circuit. This circuit, I want to look from these two terminals and find an equivalent representation so that I can connect other devices now easily to it and test or qualify these other devices alone, right? So to do that, I need to find an equivalent for what's everything inside here. First, if we look inside, we see that these are dependent sources. This is a dependent source, right? So this is a dependent source. This is an independent source. So I cannot use the trick that we're talking about to find R7, right? So the only way to find R7 would be to find the open circuit voltage, and then find the short circuit current, find R7. R7 in the Thevenin equivalent circuit is the same as R7 for the Norton equivalent circuit. And then because we're going to do the short circuit current anyway, then that short circuit current is also the Norton current in the Norton equivalent circuit. Okay, so let's go through the process. So, to find, okay, first find the open circuit voltage. We need nodal analysis to do that. So let's see. Our node is, we have one node up here, and the node voltage there is what? The open circuit, right? That's my open circuit voltage that I would like to look at. And then I have, since these two devices are connected here, I guess you can say there's a node. Okay, so what's happening at this node? If I apply Kirchhoff current law, I have current coming out here, correct? And then I have current coming out here, and I have current coming out here. If I apply Kirchhoff current law at this node up here, this is one node, and all currents are coming out, our assumption. So if all currents are coming out, I put all three currents on one side, and then 0 on the other side, correct? So what is the value of this current? Vx over 4, I have that here. Plus, what is the value of current in this branch? It's this open circuit voltage that I have, it's the voltage I have here, right? Minus the voltage at this node, right? I want the current flowing in this branch. It's equal to the current flowing in this resistor. The current flowing in this resistor is equal to the voltage on one side minus the voltage on the other side of the resistor. So it's V open circuit, right? Minus 15 volts divided by the value of the resistance, 20 ohms. Same thing with here. I want to find the current flowing in this branch. These are two resistors in series, it's like one resistor, right? So the current flowing here is equal to the voltage across the combination, which is the open circuit voltage, divided by the sum of the two resistors, which is 15 plus 5. So from here, I have an equation that relates Vx and V open circuit. So Vx is equal to 1/4 of the open circuit voltage. So this is from the, where is this coming from? So this is an equation that relates Vx and V open circuit. Now I want to find Vx in terms of the open circuit in another way, right? So similar to what we were saying in the previous circuit, there is a small trick here, right? What small trick did they apply here in this equation? Voltage divider rule, exactly. So I want to find another relationship between Vx and V open circuit. I have one relationship here. I have two variables, so I need two ways to find it. So I need two equations. So the other equation is voltage divider rule. I know that the open circuit and Vx are related. So Vx is equal to the open circuit voltage multiplied by 5 ohms divided by a combination of the resistances, right? That's the voltage divider rule. And that's what we have here. So it's equal to 1/4 V open circuit. So this is my second equation. I take this equation, I have Vx and V open circuit, so I substitute and solve for one of them, right? So they solve for the open circuit since that's what you want to solve for, right? So take your yeah, the open circuit is equal to 4Vx, put it here in this equation 1, and you're able to solve for the open circuit, and you get 4.62. Okay, so we found our open circuit voltage, but I'm trying to solve for my Norton equivalent circuit, right? So I still have some work to do. So I found my open circuit voltage, and because I had dependent sources, I need to find my short circuit current, because there's no way to find R Thevenin easily. The reason I found the open circuit voltage is because I will use that to find the equivalent Thevenin resistance. Right? So now let's see. I have dependent sources, so I put the short circuit right away. If I put a short circuit, these are resistors. Right? There's no source in this branch, so no current will flow. I have a short circuit across a pair of resistors. These don't exist. Right? So since these don't exist, now we need to find the short circuit current. So how do you find the short circuit current? Any hints? Remember, this is Vx, okay? I can do Kirchhoff current law at a node, for example. Okay? Let's try to do Kirchhoff current law at this node. If we try to do that, I want to look at what's the contribution of this branch. Fine, this branch's current is coming out. What's the value of the current coming out here? It's Vx over 4. What is Vx? Huh? What is Vx? Vx is the voltage across this resistor here. Yeah, but it's also the voltage across this resistor. It's 1 over 4. What is VOC? My open circuit voltage now has a short circuit across it. So it's 0. Right? There's a short circuit here. Or you can look at it this way. There's 0 current flowing here. So there's 0 current flowing through this resistor. So Vx is equal to 0. So this branch is gone. It's not there. Right? So I end up with what? Just a simple circuit, a voltage source and a resistor and a short circuit. So what is the value of the short circuit current? 15? No, there's no voltage divider or current divider. This branch doesn't exist. This branch doesn't exist, so it's just this voltage source, 15 divided by 20. That's the short circuit current that's flowing. So now I have my short circuit current and my open circuit voltage. So R Thevenin is equal to the open circuit voltage divided by short circuit current. Okay? So I have my all three parameters. To draw the Norton equivalent circuit, this is my I short circuit is equal to I Norton, and you put your Thevenin equivalent resistance here, R Thevenin. That's what we'll have on the next slide. Okay? That's what we have here on this slide. And remember, the polarity of the current is important, right? So current was flowing out of this voltage source into the short circuit. So that's why the Norton equivalent Norton current is shown with an arrow to the top and a positive value. Okay? Because the current that we found, the short circuit current, was in the same polarity as the Norton equivalent source that we have here. Okay, and we said we can transform between the Thevenin and Norton circuits easily, right? So because the Norton current is basically the short circuit current. So if you have the parameters in this circuit, you can move to the other circuit, and vice versa, right? So how does this help us? Let's say we have a circuit that looks something like this, right? I would like to solve this circuit. So there are two ways to go about that. So they want to find the currents I1 here and I2 in the circuit. They would like to find I1 and I2. So this is what? This is a current source with a resistor in parallel, right? How about I disconnect this from the circuit? I'll take it out. This looks like what? This looks like my Norton equivalent circuit of something, right? This looks like a Norton equivalent. This is a current source with a resistor in parallel. This looks like Norton equivalent circuit, and I know that I can convert a Norton equivalent circuit to a Thevenin equivalent circuit. What's the Thevenin equivalent voltage source? V equals IR. Right? Thevenin equivalent voltage source will be the Norton current, which is 1 amp, multiplied by 10. So the Norton equivalent voltage source will be, Thevenin equivalent voltage source will be 10 volts. Right? So this is where I split the circuit. So it's 10 volts. And the Thevenin equivalent circuit is equal to the Thevenin equivalent circuit in the Norton circuit. So I take this 10 ohm and put it here. So now I have a circuit that looks like this. With this circuit, it's very easy for me to solve for I1 in this case. I1 is equal to what? The current flowing in this circuit is equal to these are two resistors in parallel, in series, right? So I look at the voltage here and the voltage here, right? I go around the loop. So this is what? My Kirchhoff voltage law around the loop. So starting from this node, right? Starting from this node, I go minus then plus. So it's minus 20 volts. Plus 5 times the current. Plus 10 times the current. I1 plus 10. I'm seeing the positive sign first. Plus 10 equals 0. So I solve for I1 in this case, right? So I easily was able to solve for I1. Now if I have my I1 here, I would like to solve for, what's the next thing? I want to solve for I2. For me to solve for I2, actually do I need to go to that Norton equivalent circuit? I don't, right? How can I do this? I have I1. This is a node, right? So I1 plus 1 amp is equal to I2. I1 plus 1 amp is equal to I2, right? Or we could have done what? Or we could have taken this side of the circuit, change it to what? To a Norton equivalent circuit. So this is 5 is my R Thevenin, 20 is my V Thevenin, right? 20 divided by 5 is 4 amps. So my Norton equivalent current source is 4 amps. I take the same 5 ohm resistor, put it in parallel here, right? And now I have two current sources with 2 resistors in parallel. I want to find the current in this branch. How would I find it? Current divider rule. 4 amp is coming into the node, 1 amp is coming into the node. And what's coming out of the node is either going to go in this resistor or the other. So you use current divider rule to say, okay, 4 plus 1, so 5 amp is going to be divided by one of these into either this branch or this branch, depending on the resistance of the other branch. So I1 is going to equal 5 times 10, right? I1 is equal to 5 times 10 divided by 15. And then I2 will equal 5 times 5 divided by 15, right? That's the current divider rule applied. So that's what we did here. And then the last thing, if you have a box, if you've come up with the equivalent circuit and the Thevenin equivalent circuit for the system, voltage source and resistor in series. And your objective was you have a load, you want to maximize power transfer to the load. You have a heating system that is remote, and you don't care about the efficiency. Okay? Efficiency is different than maximizing power. Okay? If I want to deliver maximum power to this load, I need to choose a cable. This resistor is representing a cable. I need to choose a cable. What sort of cable would I choose? If I'm trying to maximize efficiency, what sort of cable would I choose? The lowest resistance. I agree. So we choose the cable with the lowest resistance. Perfect. 100%. That doesn't mean it's going to be the maximum power. That doesn't mean I'll be able to transfer the maximum power to my circuit. Why? We'll look at the proof. So here, if I have a simple circuit like this, just voltage source and two resistors, I would like to calculate the power across resistor. Power across the resistor is I squared times R. I squared R is the power dissipated in a resistor. Right, this I squared R. What is this I equal to? I is equal to the voltage divided by the sum of the two resistances in series. So the power is equal to this I squared times R. This is power. If I want to maximize power with respect to that's being transferred to my load, I will differentiate this power with respect to the load resistance value, and then equate that to 0. If I do that and solve, I will find that RL has to equal R Thevenin for maximum power transfer to the load, not highest efficiency power transfer to the load, maximum power transfer to the load. And so for maximum power transfer, R has to equal R Thevenin, and hence P is equal to V Thevenin squared over 4R. Where does this come from? Just give me 1 minute. Yes, I just replaced, it says just direct substitution. Okay, so I skipped that. That's good. Sally can explain it to you if you have a problem. So it's and then this is a direct application of the previous equation. So I have a circuit here. I have two terminals at the terminals of the circuit. I want to connect a load, right? And I want to be able to transfer maximum power to the load, I guess. Let's find the load resistance for maximum power transfer. Yeah. So you want to find the load resistance for maximum power transfer. You now have a system, and you want to connect a specific load to be able to transfer maximum power to that load, right? So you would do what? You would find the equivalent, Thevenin equivalent circuit for everything inside the box, and then this Thevenin equivalent circuit will have a resistance. This resistance will have to equal the load resistance that you put in if you want to transfer maximum power transfer to the load. And that's really the last slide in this chapter. So we wrapped up chapter 2. If you have questions about this last part, let me know. But the equations, I mean, direct substitution is really